All right. Good morning. So I just want to pick up from last day because we were talking about, and I'll go back there, but I pulled in kind of where we left off. Okay, but we were talking about the steps to hypothesis testing, the formal hypothesis test with a p-value approach, right? So what we said was, okay, when we use the p-value approach, oh, sorry, it's catching up here still. We have to make a few adjustments to how we check the normality condition. Of course, it's really important that we are able to assume that we can use a normal distribution, so we have to check it. And so one of the things that changes is that for our standard error, we no longer use the p-hat that we use in the confidence interval. We have a hypothesized proportion, and that's the proportion that we're going to use. Okay, and the reason for that is because we assume that the null hypothesis is true until we have proof otherwise. So let's see here. Pull up the chat. Everyone's busy having breakfast anyways. So what we do is we need to check the success failure condition, and that's going to change a little bit as well. Yeah. Oh, all done. Ready for class. Hadid it so fast. So that changes as well. So now we want to look at the expected number of successes and failures. Whereas if we're doing a confidence interval, then we just look at the observed number of successes and failures. And of course, this is a lot of stuff to have going on here, right? And so they're kind of running side by side, and it depends on what scenario you have, right? So I would encourage you to spend some time making, a cheat sheet, essentially, of all the different scenarios so you don't get messed up, right? Because in the test, and also on the assignments, but assignments you can reference things, you can look at the notes, you have time, right? And so on the test though, you have a certain amount of time, and so you want to have everything just kind of available. And I mean, ideally you would know it, right? And if you practice enough, then you will start to memorize it whether you want to or not. So we check the expected number of successes and failures, which we do using P naught, because we assume the null hypothesis, which says that P equals P naught, is true, right? And so now we're checking N times P naught, whatever your hypothesized P is it greater than or equal to 10, right? And N times Q naught, or 1 minus P naught, is it greater than or equal to 10? Once you've checked those conditions and they all check out, then you set up your hypotheses. Okay. We're going to focus on a two-sided test, and I'm going to talk about today why that is. You could do a test for less than or greater than, depending on the question, but the default is a not equal to. Okay. So for us, we're just focusing on the not equal to situation, which we call a two-sided test, okay? Because we want to look at both sides. So in step 2, instead of calculating the confidence interval, which is what we were doing, now we're going to calculate the test statistic. Now the test statistic is basically going to say how far is p-hat, how far is my sample proportion from the hypothesized proportion, assuming the null hypothesis is true, right? So then I look at the spread, and how extreme is my sample proportion compared to what I thought was happening. So once you have a Z-score, right, that's why we did all that practice. Oh, it's not coming up here. That's why we did all that practice with Z-scores, because now you know how to find areas in the curve, or areas under the curve, right? Using the Z table, for example. Pretty old school stuff using the tables, but they're definitely handy if you just have them, right? And you don't want to go on your computer to try to calculate the probability with a Z-score. your phone can have a calculator, I'm sure. So they're available, but the tables are definitely handy. Okay, so once we have a z-score, right, then we have to find the p-value. Now remember, the p-value is the probability of seeing something as extreme or more extreme than what you saw. Okay, and so in terms of, so here we have our hypothesized proportion, which is the center of our normal distribution. And then we're seeing how far is my sample proportion from that hypothesized proportion, right? And then we find the area in the tail, and that's our one-sided p-value. The tricky part is that just because we're collecting one sample, that means we're either going to be on the lower side of the curve or on the upper side. But when we're testing the not equal to case, we're interested in anything that's, you know, beyond a certain point, okay, on either side. So what we do is we kind of imagine the same area on the other side, okay? So when the alternative hypothesis is that P does not equal P naught, okay, the sample proportion will only be in one tail, right? But we need to consider that it could have happened on the opposite tail as well, right? So it could have happened on the other side. It's just a fluke that we happen to be on the one side. So from step 2, you have a z-score, and this is where we're going to pick up. So you can use the z-table to find the one-sided p-value, and then multiply it by 2 to find the area in both of the tails, right? And that will be our two-sided p-value. I wonder if I can write here, or can I do this maybe? We call this our two-sided p-value. Two-sided or two-tailed. I prefer calling them two-sided because I think of two sides, but that's fine. Or you can think of two tails. It doesn't matter. I think we're all on board. So we call this our two-sided p-value. Okay. So that was step 3, right? Finding the p-value. Now, the reason we find the p-value is so that we can draw conclusions. Okay. And so we use the p-value, right? And I mean the two-sided p-value, or simply p-value, right? So it is technically the two-sided p-value, but at this point, right, we can just call it the p-value. So we use the p-value, and it's a p-value because it's a probability. It's the probability of seeing something as extreme or more extreme. And so we use the p-value to draw conclusions about our hypothesis, to draw conclusions about our hypothesis. Okay. Which leads me to step 4, right? So step 4 is our conclusion. We know that. And we also remember that our conclusion is going to have 3 parts, right? And really only the first part changes. It's a little bit different, but we'll see here. So step 4 is the conclusion. Now, this is the part that that is really, really difficult in the beginning, okay? But the idea is if you've moved far enough out into the tails, right, then it's starting to become really unlikely that the sample proportion came from the population that you are hypothesizing, right? It's more likely that it came from some other population, right? And so as the p hat, right, moves further away or moves further into the tails, because I just want to tell you why it is that we're doing this, because otherwise, if I just tell you, oh yeah, if the p-value is small enough, then you reject the null hypothesis, that becomes really difficult to wrap your head around. And so I just want to explain what's going on, and then I'll give you the actual rule that we use. So as the sample proportion moves further into the tails, right, which would mean that the p-value is getting smaller, right? Because if you have something and you have your hypothesized proportion here, and if you've got your sample proportion out here, then this value becomes really small, right? So as you move further and further away from the hypothesized proportion, how we reflect how far away it is by this area in the tail. Now, of course, we replicate it down here as well, but let's just focus on the upper tail, okay? Regardless, we're going to multiply it by 2, so it doesn't really matter. We can just focus on one tail for now, okay? And so here, right, if this area is getting smaller and smaller and smaller, right, what we're actually saying is, okay, the probability that this p hat came from a population centered on p naught is this p-value. Now, if that's really small, then we start to wonder, okay, well, it's unlikely that it came from this hypothesized population, right? It likely came from a different population, okay? And so as the sample proportion moves further into the tails, the p-value is getting smaller, okay? And so how did I want to wrap that up here? Which means the probability that p hat came from the hypothesized population is becoming less likely, okay? So which means the probability that p hat came from the hypothesized proportion, hypothesized, I should say population, is less likely, right? Is becoming less likely. Is becoming less, let me clean up that B, becoming less likely. So it is more likely that it came from a different population. That it came from a different population. Right, which would be the alternative hypothesis. A population where the p is not equal to p naught, right? We don't know what it is, and that's kind of one of the quirks of hypothesis testing is we don't, all we can say is, well, it didn't come from a population centered on p naught. Okay, where did it come from? You'd have to build a confidence interval, right, to try to pin down where it might have come from, right? And so all we can really conclude is, well, it didn't come from that population. It came from a population where it's not centered on p naught, it's centered on something else. Notice that, right, we talked about the type 1 error, right? So there's always a p-value chance that we're wrong, right? Because there's always some probability that we have this fluky sample and it just happened to end up way out in the tails, right? And so, so that's why we can never accept a hypothesis, because there's always a chance that we're wrong. Okay, so in terms of our conclusion, what we say is, in general, if the p-value is small enough, okay, then we have enough evidence to reject H naught, right? Then we have enough evidence to say that, I don't think it came from this proportion, this population. I think it's more likely that it came from a different population, right? And so we have this idea of the p-value being small enough, okay? And that's hard to wrap our head around, but as a default, we're going to use 0.05. Right, because we had that 95% confidence interval as our default. And so we have 5% left in the tails. So basically what we're saying is if our p-value moves out past the 5% mark, and we're looking at both tails right now, right? And so if our p-value is smaller than that, so if our sample proportion is beyond those bounds, then we say we have enough evidence to reject H naught. So in general, we say if the p-value is small enough, okay, we have enough evidence to reject H naught. We have enough evidence to reject H naught. Okay, so this idea of small enough, we need some default threshold. Okay, so the default is 0.05. Okay. And this is called our significance level. Significance level, which is called our alpha level. And I could have sworn we talked about alpha last day, because the alpha level is the probability of making a type 1 error. So before you even do your test, you're saying, okay, I'm okay with making a type 1 error 5% of the time, right? There's a 5% chance that I'm making a type 1 error, and I'm okay with that. Great. So the alpha level of 0.05, that's our default. Okay. So what does that look like in terms of the curve? Well, it means that if we're centered here on our hypothesized proportion, then at some fixed point here, and maybe I'll use the same color, I've got 0.025 in this tail, and I've got 0.025 in this tail, right? Together, they make 0.05. So what that means is that there's some point here, some threshold where if our sample proportion is beyond this point, right, on either side, you have enough evidence to reject H naught. So I'm going to use the p-value approach, where we find the probability, we find the area that's corresponding to the sample proportion, and then we compare it to the alpha level. Another way you could do it is you could figure out what this value is, what proportion this cutoff corresponds to. And then if your sample proportion is beyond that point, then you could reject H naught. So there's a couple of different ways to do it. I'm going to focus on just one way, but you might see some other ways floating around, right? Where they say, okay, well, the point that corresponds to, so the proportion that corresponds to 5% in the tail is this. And because our sample proportion is beyond that point, I have enough evidence to reject H naught. So here, I'm going to reject H naught. And here you're going to reject H naught. Notice the kind of interwoven situation that we have here, right? You could build a 95% confidence interval and be 95% confident that you've built, that you've captured the population proportion. And then if you're outside that interval, then you reject H naught. We have the exact same situation here, right? Except, so here, so we have 95% here. I shouldn't be mixing my 95 and my 0.025s. Maybe I'll change that to, try not to erase everything there. 0.95. Fail to reject. And maybe I should clarify, that's a pretty common abbreviation. So fail to reject H naught. Meaning you don't have enough evidence to reject H naught. Now, that doesn't mean that H naught is true, right? It just means that you haven't found enough evidence to reject it. So we don't actually know what's going on. And so usually we say, instead of fail to reject, we usually just abbreviate FTR, fail to reject H naught. Okay, so in general, if the p-value is small enough, we have enough evidence to reject H naught. So as a default, we use 0.05. So if a question doesn't say what significance level to use, then you use 0.05. If it says use an alpha level of 0.1, okay, what does that mean? It means that you're going to move your threshold closer to the hypothesized value, making it easier to reject H naught, right? Whereas if you move it further out into the tail, so let's change it to 0.01, right? Then it becomes harder to reject H naught. Okay. If a question doesn't say what significance level to use, we use alpha equals 0.05. Right, and then I want you to just consider alpha equals 0.10. If I increase the area in the tails, right, so I move the threshold closer to the hypothesized value, then I'm moving these bounds closer in, right? And so it makes it easier to reject H naught. Or alpha equals 0.01 makes it harder to reject H naught compared to 0.05, of course. Harder to reject H naught compared to 0.05. Compared to alpha equals 0.05. Okay. So that's just something to keep in mind. So remember, the significance level, the alpha level, is the probability of making a type 1 error. So if you want it to be sort of, if you don't really care about making a type 1 error, maybe it's, you know, you're deciding your favorite restaurant and it doesn't really matter, right? Something kind of inconsequential, then you can adjust it and you can make it 0.1 if you want. But if it's going to be super expensive to make a type 1 error, which is when you reject H naught when it shouldn't be rejected, right? Then you have to adjust the alpha level to 0.01 maybe. These are kind of the key 3 players that we use. You could use whatever you want, but these are kind of the standards. So if you want it to be hard to make a type 1 error, then you would reduce the alpha level. right? Or if it's expensive, right? If you want to look at making changes that are going to cost your business $1 million, you want to be really, really sure that you're not just doing it for no reward, right? So things like that. Okay, so our conclusion, we've talked about kind of what goes into it, okay? But our conclusion still has 3 parts. Okay. So our conclusion still has 3 parts. First one being, you have to compare your p-value to the alpha level, right? Is it less than or is it greater than? Or usually what I say is it less than or not less than the alpha level? So compare the p-value from step 3, right? To the alpha level. Oops. And here you have option, maybe I shouldn't call them A and B. I'll just call them like this. So here, the p-value is less than the alpha level. Okay, and you'd want to back it up with the values, right? Because sometimes you might catch yourself saying something that doesn't make sense. Something like, since 0.064 is less than 0.05, no, that's not true, right? And so you want to back it up with the values. So 0.0064 is less than 0.05, right? So then you have that support, right? So the p-value is either less than the alpha level or the p-value is not less than the alpha level. Okay. So then the second step is to state the conclusion in terms of the null hypothesis. So notice how that's the same step as before, right? But it's going to depend on the p-value. So state the conclusion in terms of H naught. So depending on what you did here, copy, paste. So if the p-value is less than the alpha level, you have enough evidence to reject H naught, right? If the p-value is not less than the alpha level, you do not have enough evidence to reject H naught. Maybe I'll separate these. So the first one, the p-value is less than the alpha level. You have enough evidence to reject H naught. Oops. To reject H naught. Whereas if the p-value is not less than the alpha level, right, meaning that you're not past that threshold, so you're close enough, you're kind of hanging out where those expected proportions are. Okay, so if it's not less than the alpha level, you do not have enough evidence to reject H naught. Yeah. Okay, so that's hard to remember. And I've got this admittedly borderline, but very helpful meme. Snoop is going to help us out. So if the p is low, so if the p-value is low, then the null hypothesis must go. Yeah. Yeah, you'll never forget. It's one of those things that it's so stupid, but it's so useful because, oh, you read that wrong, did you? Well, might help. I can't read it wrong. Yeah. Okay, so borderline not okay to share, but I do think it's really helpful. And there's so many, if I'm marking final exams, I always kind of see it scribbled in the corner somewhere. They had to get it out, you know, if the p-value, okay, if the p is low, then the null hypothesis must go. And so I know it's useful, so that's why I keep sharing it, even if it's a little bit inappropriate. So, but really helpful, I think. So to help you remember. Okay. So it helps because there's a lot of ins and outs, right? And so the key part is, what do I do? Okay, so you have to compare your p-value to the alpha level because that's implied here. What is low, right? If the p-value is low, well, it means that the p-value is less than the alpha level. And so then you have enough evidence to reject H0 in favor of HA. Okay, good. One final thing that I want to talk about just in general is we can do one-sided tests, okay? But what becomes a little bit difficult is once you've decided to do a one-sided test, right, then you're only focusing you're focusing on one of the sides, right? And so anything interesting that happens on the other side, you have to ignore, right? And so so you can lose a lot by doing a one-sided test. Now, that said, for a one-sided test, because sometimes we'll include one-sided tests because, you know, we want to have a variety of questions and we don't just want to look at, is there a difference here or has there been a change here, right? We want to talk about, is this proportion less than the hypothesized proportion, yes or no, right? Or is it more than the hypothesized proportion, right? And so a little bit of caution. Okay, so we can, and maybe I shouldn't have them so big here. There. Boy, what happened there? Delete, start over. We can conduct one-sided tests. Okay. And sometimes we do for a variety of question types, right? But in reality, right, then we should only be doing two-sided tests. It's pretty rare that you should be doing a one-sided test. Okay, so we can conduct one-sided tests, such as H0 is that P is equal to P0, that stays the same, but the alternative hypothesis is that P is less than P0. In this course, and for simplicity's sake, because we can rewrite this, if this is P is less than some P0, then this could be greater than or equal to, but for simplicity, we keep this as an equal to. Keep this as an equal sign. Okay, so now this is a one-sided test. Because what we're looking at is something like this. Oops, why is it doing that? So we've still got our hypothesized proportion in the center here, but is P less than P naught? Right, so is this somewhere down here? So then this would be our one-sided p-value. Notice how you put all your eggs in one basket, as opposed to in the two-sided test, we would replicate that. We kind of pretend it happened on the other side as well, right? So now, right, now we have a threshold. We put all our significance level on one side, right? So these can happen, and it's going to depend on the question. Or we could have the other side where H naught P is equal to P naught and HA P is greater than P naught. So again, it's a one-sided test. So we have P naught, and I'll try to use the same kind of color scheme here. So this is the one-sided p-value. And this is what makes it a one-sided test. So now we don't have to replicate the p-value in the other side, right? But we also have to ignore if it could have happened on the other side, right? And so I will say this, that although the questions that we have in this course that we use and we talk about in this course are going to consider one-sided tests just for variety, right? In real life, you should just be using two-sided tests, because you don't want to open yourself up to, oh, I can only make conclusions about the one side, right? But there happened to be something interesting on the other side, right? And so, although we consider one-sided tests for questions, although we consider one-sided tests in questions we solve in this course, in practice, right, in reality, we should really only be using two-sided tests. In reality, we should only use two-sided tests unless there is some reason to completely ignore anything that happens on the other side, right? And so unless there is some reason to completely ignore outcomes on the other side, right? That's rarely the case. Okay. So you should be prepared to pick up on one-sided tests and two-sided tests from the questions, but in reality, right, and that's just for practice, just so you know what to do if you wanted to do that, right? But in reality, if you're ever kind of, how do I set up my hypotheses? you should do a two-sided test. Okay. Okay, good. So let's see here. I think I had an example. Oh, and I also posted, before I bring up that example, I posted these notes. They're kind of outdated because they're from when we did means questions before proportions, but now we're starting with proportions. So it starts off a little bit weird, but I posted this so you would have a summary, and also just a summary of the assumptions, just kind of on one page, right? And so it differs if you have a hypothesis test versus a confidence interval. And so talking about the hypothesis tests. So in general, this is what we were talking about. I'm not going to use this example. I want to use a different example, but I have it shown how you could do it in R if you don't want to do it by hand, right? And so this one's a little bit of a tricky question to think about, but goes through and it talks you through how to check your assumptions and all that fun stuff. So talks about the p-values. So you have that example, and also this is where I stole this example from that we worked through. So we've already seen this one together, but here it is worked out for you. Okay, and so I want to do an example that I stole from the textbook. Oops. Okay. So I'm going to go through this one a little bit quickly, right? Because we have talked about this, and we do know how to calculate Z scores, and we do know how to do all this stuff. And so it's not really that hard. It's just a lot of components that we have to keep together and do in a certain order. Okay, so if we want to solve this example, so a simple random sample of 1,028 US adults in March 2013 show that 56% support nuclear arms reduction. Does this provide convincing evidence that a majority of Americans supported nuclear arms reduction at the 5% significance level? So this is one of those cases where we have to understand what a majority means in terms of a proportion. So a majority is more than 50%. Okay. And so here, I'll do it in, sure. Majority, oops. Is more than 50%. I think they would probably treat it as a two-sided test, right? In terms of when they go through it in the textbook, but I'm going to say it's more than 50%. So we're going to do it as a one-sided test. Okay. But then I'll talk about, you know, if we wanted to test the two-sided, then we would just multiply the p-value by 2. So first thing we have to do is we have to identify all the information that we have here. And so first things first, I have N is 1,028, right? That's my sample size. I have a sample proportion, so P hat is 0.56. Oops. Yeah. My P naught is this 50%, right? Is 0.56 significantly larger than 0.5? And that's what we're trying to find out. And the alpha level here, alpha is 0.05. So first thing we're going to do is we have to check the assumptions. So before you do anything for a hypothesis test, so before you can even start a hypothesis test, you have to check the assumptions. So check the assumptions. I'll say check the assumptions for inference. Right, and we're doing a hypothesis test in this case, right? Because we want to know if at the 5% significance level, is there evidence that a majority of Americans supported nuclear arms reduction, right? And so we're going to do just a flat out hypothesis test. How would you do this if you wanted to do a confidence interval, right? It would ask for a confidence interval. So I don't want you to be taking liberties, but at the 5% significance level, you would make a 95% confidence interval. However, because I'm talking about more than 0.5, okay, then everything goes out the window. Then I can't do a confidence interval because the 0.5 or the 0.05 would all be in one tail, right? You could do it, but you'd have to think about a confidence interval. So now you would have 0.05 in each tail. So you'd make a 90% confidence interval. So you'd have to be really, really careful because now we're doing a one-sided test. So because we want to know if there's more than 50%. Okay, so check the assumptions for inference. And we're going to do a hypothesis test, right? Because as soon as it says the 5% significance level and it doesn't say make a 95% confidence interval, then you're going to do a hypothesis test. So the first thing we have to check is independence. And in those notes that I posted, it also checks the less than 10% condition. We've made that optional now, so but it's something to keep in mind, right? Your sample size has to be less than 10% of the population in order to be considered independent. But it says that we took a simple random sample of 1,028 US adults, and so we are also comfortable saying that 1,028 is less than 10% of US adults. And so the first thing, right, sample was randomly selected and optional. N equal to 1,028 is less than 10% of US adults. In 2013. I should say March, but I ran out of room. Okay, so if you want to show off, you can check that one. But it's good. How do we know it's less than 10%? We just assume. But also, you know, you think about the population of US adults and is 1,028, is it reasonable to assume that it's less than 10% of US adults? Yeah, it is, right? And so, so even if you don't know, right, we would say something like, it is reasonable to assume that N equal to 1,028 is less than 10% of US adults. Right. But if you want to skip it, it's okay. Nice. So that's the independence part, right? So the sample is randomly selected, so we can assume that they're independent. Now, for the normality condition, for a hypothesis test, remember we check the hypothesized number of successes versus the hypothesized number of failures, or the expected number. And so to check the normality condition for a hypothesis test, we need the hypothesis or the hypotheses. So we can set that up. That's step one of our hypothesis testing, but we can do it and then redo it, sure. So one thing to remember is that you're always going to have an equal sign in your null hypothesis, right? And so P, it has to be about the parameter P. And in this case, P naught is going to be 0.5, right? So if there's no change, no difference from just half do and half don't, right? So then 0.5. Versus the alternative hypothesis is that P is more than 0.5, right? And so, and maybe I should write this the other way around here. Maybe I'll do 0.50 just to make it look a little bit nicer. It doesn't matter, right? So this is saying that P naught is equal to 0.50. Okay, and it's because this is a majority. So is there evidence that P is larger than 0.5, right? A majority. So from here, we need to check our assumptions. So N times P naught, which is 1,028 times 0.50, which is just half of that. 1,028 times 0.5 is 514, which is greater than or equal to 10. So I'm going to do a little green check mark here. N times Q naught, remembering that Q naught is just 1 minus P naught. Those Q's, I use those as shortcuts, and I'm going to start doing that more and more often now because it's good to get used to seeing it. And you'll probably want a little shortcut as well. 1,028 times technically 1 minus 0.5, but I'm just going to go for 0.5 is still 514, which is also greater than or equal to 10. Like I said, these will always check out. It's just we have to remember to check them. So therefore, the assumptions for inference are satisfied. Are satisfied. Okay. Good. So now we're ready to actually set up our hypotheses and do the hypothesis test. And so step one is state your hypotheses. We already set it up. So because we had to know what P naught was to check our assumptions. So we actually already have this. And so I'm going to jot it down here. H naught is that P is equal to 0.50 and HA is that P is greater than 0.50. I'm going to highlight that this greater than makes it a one-sided test. Okay. We don't need that until we get to step 3, where we actually need to calculate the p-value. And so there's that disconnect, which throws people off a lot of the time. You get to step 3, and how do I know if I have a one-sided or a two-sided test? Well, you have to go all the way back to step 1 and look at it there. Okay, so now step 2 is do the test. You don't have to outline the steps, but you do have to do them all. And so we have Z is P hat minus P naught over the root of P naught times 1 minus P naught over N. And in case you've forgotten, where is that formula sheet? Did I bring it in here? I posted it on Moodle, but where would I have it? Oops. Bring it in here. Oh, of course it's old. Scribble on it to bring it to the top. So the order is all screwed up on here. Wow. But if you go to the second page, right, you have one sample proportion, you have the hypothesis test, and it has the Z score that you're going to calculate. It also has the confidence interval. So paying attention to whether you have a P naught and a Q naught or a P hat and a Q hat under the square root, right? And then it depends on if you're doing a hypothesis test or a confidence interval. And so it's all here, right? And I even have a note that Q is 1 minus P in general. And so just remember that you have that available to you. So in our case, Z is going to be 0.56, right? Because that's our sample proportion. How far is it from the hypothesized proportion of 0.50? So in terms of what we're looking at is we've got our hypothesized proportion of 0.50. How far is 0.56? Right, and then in step 3, we're going to find this area, which is our one-sided p-value. But we need to know the spread, which is the standard error, but it uses the hypothesized proportion because we assume the proportion or the hypothesized proportion is true. So 0.50 times 1 minus 0.50 over 1,028. So I go, well, 0.56 minus 0.5 is easy enough. I get 0.06, and then 0.5 times 0.5 divided by 1,028. Don't forget to take that square root. I'm going to do that right away. And I get divided by 0.01559457,154. I'm going to keep all those decimal places. There's no harm in jotting them all down. So now I'm going to do 0.06 divided by that. And so I get a Z of 3.84749,269. Z, we round to 2 decimal places, right? Because our Z table, if we're using a Z table, can only handle 2 decimal places, right? And so Z is 3.85 to 2 decimal places if we're using the table, which we are. We already know just from using the Z table from before, we know it maxes out at 3.49, right? We're going to look and just confirm that, but what we're going to find is that the area in the tail is less than 0.0002. Remember when we started talking about Z scores, we said, okay, any Z score greater than plus or minus 2 on either side is going to be considered extreme, right? And so here I have this relatively large Z score, so it's more than 2. So I already suspect I'm going to be rejecting H naught, right? That's what I suspect. Okay, but in step 3, find the p-value. Okay, so now I have this Z distribution. And so here, of course, I'm centered at 0. And I found a value of 3.85. Okay. And so using the Z table, we find, okay, where's the table here? So I'm on the positive side of the Z table, and now I'm trying to find that 3.85, and I go through and I look, and it looks like I max out at 3.49, right? And it looks like the area to the left is 0.9998, meaning the area to the right is 0.0002 at 3.49. Okay, and so here, what we found is that the table goes to 3.49. And what we could do is we could find that this area is 0.0002. Okay. So what we're going to say is that this area, this one-sided p-value, is just less than 0.0002. So less than 0.0002. Because it's past that threshold. Okay. Just to show you what I mean by using, it's called the critical value approach. And so what you could do is you could force the area in the tail to be 0.05 and find what the Z score is that corresponds to that. And then because our Z score is larger than that, so it's beyond that point, then you can reject H naught. So, but I'm going to stick to this approach, but that's what you could do here, right? So using the Z table, we find the one-sided p-value is less than 0.0002. I noticed in the textbook, they use the rule that if you're beyond that point, you just say it is 0.0002. I like to be a little bit more flexible because it doesn't really make sense to me to say that it is 0.0002, but it's less than 0.002. But even if you had to find a two-sided p-value, it would be less than 0.002 times 2, right? So it would still be really, really, really small. So now for our conclusion, most important part. And maybe what I should do here is I should say what it would be for a two-sided test. If we had HA is that P is not equal to 0.5, which is a two-sided test. The two-sided p-value would be less than 0.0002 times 2. The two-sided p-value would be less than 0.0002 times 2. Which I'll do in brackets here, less than 0.0004. Okay, so regardless, we're going to have a really small p-value. Okay, so the conclusion, you want to state how does the p-value compare to the alpha level, right? So remember, the alpha level is 0.05. I think it said use a significance level of 0.05. I'll catch up here. So 0.05 is our alpha level. And also I'm going to just snag this little last part temporarily because I just want, for my very last part of the conclusion, I just want to reformulate the question as an answer. So we're not doing anything crazy here. Maybe we are, but not intentionally. So the conclusion. So since the one-sided p-value, p-value is less than 0.0002, right? It is definitely less than the alpha level of 0.05. Okay. So it is definitely less than the alpha level of 0.05. Yeah. Which means, so our P is low, so we can reject the null hypothesis. It's got that nice ring to it, right? So if the P is low, then the null hypothesis must go. And so since this is so small, we have enough evidence to reject H naught. So it's less than the alpha level of 0.05, which means we have enough evidence to reject H naught in favor of HA. That's just kind of a completeness thing. You don't have to say the in favor of HA because you only say it if you're rejecting H naught. So what does that mean? Well, in terms of the question, does this provide convincing evidence that a majority of Americans supported nuclear arms reduction? Yes, there is evidence that the majority of Americans supported nuclear arms reduction, right? And so that would be your conclusion in terms of the question. So we conclude there is evidence that a majority, of Americans supported nuclear arms reduction. Okay. So I'm going to remove this because it's just a random blip here, but it does help, right, to formulate the question as an answer to do that last bit of the conclusion. So first part of the conclusion is comparing the p-value to the alpha level, right? That's part one. Part two is your conclusion in terms of the null hypothesis, right? Based off of that p-value, oops, I went too far. Based off of that p-value, what's your conclusion in terms of the null hypothesis? Can you reject it or can you not reject it? And then finally, you have to state your conclusion in terms of the actual question. Yeah. Good. So that's the ins and outs of confidence intervals hypothesis testing for one sample proportion. The last thing I want to talk about for one sample proportion is it's pretty common if you are setting out to do a study, right, that you want to find, okay, well, what sample size am I going to need? Right. And so what we can do is we can do sample size calculations before we collect any data. Right. And so this is kind of the end of that. The end. Sample size calculations. And I'm actually going to grab it from those notes, the chapter 6 notes that I posted, but they're going to be kind of in the middle somewhere. And we're just going to talk about it here. So if you're designing a study, so before you even go out and collect any data and you have a sample proportion, right, you might need to calculate the sample size necessary to satisfy some margin of error restraints, right? So remember that the margin of error is this plus minus chunk in the confidence interval, right? And so here, that's your margin of error. So how wide are you allowing the bounds to be? Okay. And so what we do is we can say, okay, well, I could calculate the sample size that I would need. Oops. Okay. So if we let the margin of error to be denoted by a lowercase m in this case, then we could rework this and solve for n, right? Because if we remember here that, okay, we're going to let the margin of error be denoted by just a lowercase m, then we can set m is equal to z star times the root of p hat q hat over n. So if I rework this, right? So I divide the z star over, and then I have a square root, so I need to square both sides, and then I'm trying to solve for n, so I multiply it over, and then I divide everything else over. And what I end up with here is this formula. That formula sheet that I posted, that's at the top of your Moodle page, has this formula. So you don't have to worry about deriving it every time, although you could pretty easily, right? So what we find is we're on the formula sheet, right? We have this. Notice the difference here is that P star Q star. Now, if I look at this, remember we didn't have, so this is before we collect a sample. How am I supposed to have a sample proportion if I haven't collected a sample, right? So here, and maybe I'll use kind of this green. Notice that we need P hat, right, and Q hat, but Q hat is just 1 minus P hat, so we still just need P hat, but we haven't, but this is before collecting a sample. So we have two options, okay? If you want a conservative estimate, the most conservative estimate for n is going to be a 50-50 split, right? P hat equals 0.5, okay? And so we have two options. Okay, and what I want to show here is I've replaced the P hat Q hat with P star Q star, and we actually have two options for P star and Q star. In general, we write P star instead of P hat. Okay, so we have two options for P star. Option number one is the most conservative estimate is P star equals 0.5. The most conservative, so basically the largest possible sample size, because you want to be really safe. The most conservative estimate uses P star equal to 0.5, which means that Q star is also 1 minus 0.5, which is 0.5. Okay. If you have some prior knowledge, so if you've collected past samples, you could use those sample proportions. Okay. So with prior knowledge or prior samples, we could use a past P hat. So then P star is equal to some P hat from a previous study. Yeah. So just before I completely run out of time here. Okay. It goes through and it talks about the exact same thing. But what I want to show is in this example, right? If we had this exact same example and we calculate the confidence interval, really what we're saying is the margin of error here is 0.0245. Okay, so what if we wanted to reduce it to 0.01, making our estimate even more reliable, right? Even more steady. So then here, determine the sample size required using the sample proportion as preliminary data. What does that mean? It means that P star is going to be P hat from that previous sample, right? Because now I'm just adjusting the margin of error. And then determine the sample size required, assuming that you have no preliminary data. So that's when we use that conservative estimate. So here, this is when P star is equal to that sample proportion, which was 67%, right? 0.67. P star is 0.67. And then assuming you have no preliminary data, then you have to use the most conservative approach of 0.50. The last thing I want to say is you always have to round up your N. So even if you get a decimal of 0.01, you can't survey 0.01 of a person. And so you would have to round up just to be safe. Okay? And I'm going to find that note somewhere here. So I want you to try those questions on your own, and that's where we'll pick up. But the solutions are in the notes, so we'll just kind of go through it pretty quickly tomorrow. It's tomorrow already, crazy. And that'll be good. Okay. So we'll need to round up to the nearest whole value. And just some things to keep in mind. Now I'm way out of time. But if you have any questions, let me know. Otherwise, I'll see you tomorrow morning.